In this session, we're going to move on to look at distributions. So hopefully you've already had a chance to watch the short YouTube clip, which talks about it in a better way than what I can. This idea of how we get slightly different looking distributions in our data when we're talking about continuous types of data, and also how we get this idea of skew or skewness, where we get a sort of a weird kind of shape beyond what we class as being the normal distribution. And we'll kind of touch on that a little bit as we go through the material too. So in terms of how we look at distributions with our continuous data, so interval or ratio data, we have the histogram as one of the tools available to us to visualize it, to allow us to look at the pattern, get a bit of an idea about what's going on. And this graph shows the age of respondent in a survey of about 1,500 people, and each one of the measures here is the number of individuals within that group. So here on the y-axis on the left-hand side, it shows 100 or 200 or up to 300 people could be in one of these age groups. So in these kind of 5 age bands from 20 to 25, 25 to 30, and so on. So you sort of see, for example, that you have increasing numbers as you go up ages until you get to a peak of age kind of 35, and then it starts to drift back down, almost in a kind of similar sort of pattern from the increase. So almost in this first half of the graph, you get a normal distribution where you've got the balance of where the mean is right in the middle, and then you've got a balance either side of that. So that's the normal distribution you'd have. But here you can also see that there's obviously this long tail that goes away to the right hand side as we have other people, older people in the group in this survey as well, but we just have less numbers of those, and then as you start to get to the very older ages, it starts to dwindle down into quite low numbers. And this graph, this histogram, helps also reflect why we use the different types of average, so the mode, the median, and the mean, in terms of the value that it offers us. So the mean works really well when we have that normal distribution. It gets us where that kind of balance is, right in the kind of essential the midpoint, the middle of the averages, whereas the median is much more effective when we don't have that same normal distribution. We don't make that assumption that we have an equal kind of, or roughly equal numbers of lower values to the mean and higher values to the mean. So the median then comes into play and allows us a little bit more information, a bit more reliable information when we use that with this type of non-normally distributed data that in this case has this long kind of tail on it. And also we can use the mode as well under certain circumstances too, but as we've spoken about, the mode is probably the least effective of the measures. Typically we would focus on the mean or the median where possible to use them. Another example, same number of people, same survey, roughly speaking, although not everybody answered the question here, so we've just got slightly under the numbers we had in the previous histogram. And this shows us the same distribution. And here you can see, again, it's very strongly non-normally distributed. So previously, like the kind of graph we saw before, you have the numbers kind of increasing at the lower values and then tailing off. So you have this skewness to the data. So it's what we could call asymmetrical. So it doesn't have that balance either side of what we would class as being the mean here, which is 3.9. The median is probably somewhere closer to 3. If we kind of look where all the kind of values lie there, and the mode as well would probably be around about 3 too. So this has what we call a positive or right skew. So that when we use those words, when we use that term, it tells us about the direction of it. Is it the higher values that have this kind of tail at the end, or is it the lower values that have this tail at the end? In this survey, which is a slightly different study, which is looking at how many miles to the gallon do people get in their cars. Here we see a distribution of responses, which is approximating a normal distribution. So it has this bell-shaped kind of curve, is what we call it, the normal distribution, whereby we have the majority of the values in around the kind of mean values, and then we have a relatively balanced tail either side. Now, obviously, you can see from this, we've drawn a best fit line of this normal distribution through the data. Now, it's not perfect, and very rarely are you going to get a perfect normally distributed kind of data set. So this is what we'd say is approximately normal. It has a rough kind of shape. Obviously, you've got some of those values between about 14 and 20, which don't fit perfectly within that. But broadly speaking, we've got a balance of numbers on the lower end of the scale, numbers on the higher end, and the majority of the values towards the kind of middle points of the data that we have. So these are the different distributions that we might encounter. And it's important to understand this and understand our data, particularly when it comes to those kind of continuous interval ratio measures as our outcomes. It's important because the dependent variable, so the outcome variable that we have, in many statistical tests is assumed to be normally distributed. There's also a number of other assumptions that we make in some of these statistical models, but the key one, particularly for the stage that you're at, is to understand that there's an assumption that this data is normally distributed. So it has that bell shape, it has roughly equal numbers of smaller values, roughly numbers of higher values, either side of the kind of mean or median. And these are known as parametric tests. We have an alternative known as the non-parametric sort of suite of tests, which we can use if we have a non-normal distribution. There's also things we can do to the data to try and make it fit a normal distribution. There's some kind of calculations that we can do. We can modify the scores a little bit if we need to, in order to try and get it closer to the normal distribution, if that is what we're aiming for. But there are tests either side that allow us to use the normal parametric types of tests and the non-parametric tests. And it's something we're going to look at in a little while, about some of the alternative tests that are open to us for that. In reality, to be honest, it does get a bit more complex, and so I've provided a Minitab blog on the page that you can go and have a read of, which talks a bit more about parametric and non-parametric tests and what some of the assumptions are built in around them and why we use them essentially. So we have statistical tests that allow us to assess normality before we then go and do the kind of next more analytical inferential types of statistical tests that we want to do. Now, these are known as the Kolmogorov-Smirnov test and the Shapiro-Wilks test. Both determine whether the underlying distribution in our outcome, if it's continuous data, is normal, and it should be used in conjunction with histograms, and we'll kind of explain why that's particularly important. Because both tests are sensitive to outliers and can be influenced by sample size. For smaller samples, non-normality is less likely to be detected, but the Shapiro-Wilks test is generally a bit more sensitive, so we tend to use it with a smaller sample. By smaller and by larger, again, it's a little bit of a kind of arbitrary cut point, but we're speaking generally here about samples that are about under 100, we would class as being smaller samples. Sample above 100 would be classed as a larger sample. And when it comes to those larger samples, we've got the kind of flip, if you like. So the normality tests here are overly conservative. So actually trying to get a statistical test that shows the normality in the data, it's actually a little bit difficult, and often you might get it rejected for some of those variations. So if we think back to the histogram we showed that we said it was approximately normal, that if you were to run one of the normality tests on a larger data set would probably come out saying it's not normally distributed by the statistical measures, but we can see with the histogram that it's much closer to a normal distribution than it is to a non-normal distribution. So normality of histograms, or what we also know as QQ plots, you don't need to worry about them too much just now. These are where we start to look more at the visual sort of attributes as opposed to the tests that we can run. Now, those tests offer value, we can look at them, we can use that information, but as I mentioned, for these larger samples it can be a little bit kind of conservative and doesn't quite tell us what we're looking to do, so it's more valuable when we're using very small samples of under 100. And with these tests that we run, the Kolmogorov-Smirnov test or the Shapiro-Wilks, we're looking for essentially a non-significant result. So we're looking for a p-value that's above 0.05, and we'll cover p-values in a bit more detail later on when we look at statistical testing. But for this stage, all you're wanting to know is when you run your test for those smaller samples, if your p-value is greater than 0.05, then that tells us that the data is likely normally distributed if it gets that value. So that the higher the p-value, the more confident we can feel that the data has a normal distribution. Now, I've provided a worksheet that you can look at that's by a group called StatsTutor, which talks a little bit more about normality tests and particularly has data on it linked to SPSS and kind of runs you through an example of how you run it and how you interpret the outputs from that. And so have a look at that, make sure you familiarize yourself with it, and it'll help you with the exercises, with the assignment, and your understanding going on as well. It's always one of those ones that I have to remind myself about the p-value or how it quite works in the normality testing, just to when I go back to look at it to start again. It's one of those things I always forget, to what exactly the test means. So it's always useful to have these worksheets or these reference materials we can look back at just to remind ourselves what we're actually looking for. And so that's what you're going to do now. Once you've had a read of the Stats Tutor materials, is have a look at exercise 3, where we're going to run some of those normality tests. We're going to run some histograms as well, so we can look at distributions in our continuous measures in our data set, and then also compare those in terms of how they look visually to what these normality tests will throw up.